Thank you so much for joining us today for our conversation around machine learning and how you can leverage it for your business. And before we get started, I want you to be aware that there's a chat bar that I just typed something in that you can submit your questions as they come up. At the end of the webinar, we're going to have about 5-10 minutes for a Q&A. So I'm going to earmark your questions throughout the session. So don't feel like you have to hold off until the very end. Feel free to ask them along the way. We have two speakers with us today. Joe Intrakamhang is a senior solution engineer and machine learning expert at Google. Google's been making massive strides in ML in the last few years. A notable example there is how they incorporated ML in their G Suite applications like Google Slides and Sheets for a more seamless experience. We also have Paul Lundberg with us today from Agosto. Agosto is one of the top premier Google partners in North America and was recently awarded by Google as the top partner for their custom solutions built on Google Cloud platforms, specifically around the Internet of Things and the machine learning spaces. So Paul Lundberg is the CTO of Agosto, and he brings a wealth of knowledge from his work with Fortune 500 companies and small companies alike. Something to note also before we get started is that Paul and Joe will be sharing some insights they gleaned from customers and trends in the space. But if you want a personalized consult from the machine learning experts at these two companies, I'm going to provide my email address at the end of this webinar, and I can connect you with the ML teams at Agosto and Google, and they can evaluate your pain points, goals, current workloads, and then process and collaborate with you to create a strategic vision for how machine learning could impact your specific company. So if you want to grab my email address at the end, or if you can't stay until the end, you can also respond to the invitation you got for this webinar, and that will work as well. So moving on, you didn't show up here today to listen to me talk, so I'm going to hand things over to Joe and Paul. And again, if you have any questions, feel free to put them in the chat bar.
Thank you, Christy, for the introduction. My name is Joe from Google, and I want to start off with one of the most recent machine learning apps that came from a TV show called Silicon Valley, the Not Hot Dog app. The purpose of this app is to tell a picture whether or not it contains a hot dog or not. And for some reason, my 4-year-old daughter is in love with this app. It's always taking pictures of random things around everything to see if it's a hot dog or not. This app was written using TensorFlow, which I'll be describing later, and it's ran on a mobile phone. Mark Cuban recently stated this year, artificial intelligence, deep learning, machine learning, whatever you're doing, if you don't understand it, learn it, because otherwise you're going to be a dinosaur within 3 years. Mark is making this grand statement because machine learning is becoming more accessible to everyone, and it's not a new computer science. This is a chart, and it's not Google's profit chart, but it just shows the number of machine learnings being deployed within Google. And as you can see, our deep learning models have reached over 4,000, and we're greatly accelerating over the past few years. So at a high level, I just want to make sure that we're all on the same playing field. I'm going to go over this very briefly. What is machine learning? Oops, sorry. So as the quote stated, machine learning is not a new computer science field. It's been around. It's giving the computer the ability to learn without explicitly being programmed. So we have data that feeds into algorithms that generates insights. In reality, machine learning is collecting data, organizing data, and creating data. And we're in fact finding that 70% of the machine learning work is just around the first 3 areas. And it can't be just as easy as data plus algorithm plus insights. So how it works is that if you take the hot dog app, and that's one of the main areas that we're seeing right now in machine learning is image classifications. And there's 2 ways. How do you teach a computer to do it? There's 2 ways: supervised learning and unsupervised learning. With supervised learning, you feed it 1,000 images with labels saying that it's a cat or it's a dog, And in this case, the computer will break down those images into numerical data points or dimensions, and it flows through a neural net and process the data until eventually we get a probability that it is a dog or a cat. Unsupervised learning is the other way, where we're clustering data based on the features that we're looking at. So if we take one feature of just maybe the colors on the eyes on the right-hand side, you can't really tell that if it's a dog or a cat. But as we add more features, we're able to cluster things a little bit better. So if you take this example of a dog and a mop, it's a little hard to tell. It's not as easy as it is. So some pictures, it can be a little deceiving that it's a dog or it's a mop. And the more images that you're able to feed and give clean data to it, the better that we're able to predict the outcome. So let's have a little fun with this. If the participants can put in the chat whether or not this is Tom Hanks or Bill Murray. 5 seconds or so. So our Google Cloud Vision API says it's Bill Murray, and it's right. It's Bill Murray making a facial expression that looks like Tom Hanks. So I want to go over some use cases within manufacturing that we're seeing within the industry itself. A few to highlight are assisted technician, predictive maintenance, and resource optimization. So for assisted technician, the picture on the left is showing Google Glass being piloted with Boeing to help build airplanes. Boeing's research and technology division said that they used original Google Glass to construct aircraft wire harnesses. Because planes contain hugely messy and complex webs of wires to connect electrical systems, technicians have to manually build them out, a painstaking process based on PDFs, assembly guides viewed on laptop screens. With glass to replace the computer display, Boeing says that it's reduced the production time for the harnesses by 25% and cut the error rates in half. The Skylight app is filled with machine learning and by allowing the glassware to scan a QR code, which pulls up the wire harness software, and then scan another QR code to get the assembly instruction. And the app also supports the voice commands and also lets users stream what they're seeing to another technician in the event of something unexpected. Another example of what we have is predictive maintenance. Predictive design and maintenance. Verisoft's quality inspection suite helps you engineer a component into a 3D model to be able to run simulations, allowing the designer to modify configurations and seeing possible failures without actually having to build it. Another trend that we're seeing is resource optimization. This is where the system takes data from various sensors throughout the manufacturing process, and the machine learning algorithm helps optimize the workflow, energy consumption, inventory, reduce some rework, and smoothens orchestration and activity. So I'm going to be turning this over to Paul from Agosto for this use case.
Hey, thanks, Joe. Those are really good trends and use cases. Hey, everyone, Paul Lundberg again from Agosto speaking. As mentioned, Agosto is a Google Cloud Platform partner. We spend a lot of time developing on Google's platform. In fact, it's really the only platform we develop on. We began building our expertise in machine learning following several of our Internet of Things solutions and products that we built. A very common commercial need in IoT has been in the area of fleet management, so managing commercial vehicles. So I'm going to just describe a little bit about how we found our way into machine learning. In the lower right, you see an architecture diagram that if you generally look left to right, you'll see that there's data flowing from vehicles into multiple types of device clouds. We then go through kind of a data normalization process and then into an event processing pipeline. And this is a very common pattern that you find in IoT, regardless of what type of data it is. What we're really trying to do is take data, collect it, and transmit it to the cloud. In many cases, this data already existed on devices and just wasn't being transmitted and made available to the cloud. And in other cases, we're working on deploying new devices that are moving different types of data to the cloud. In any case, once we're able to collect the data, we can start to do really basic data processing and alerting, analytics, those types of things using that data. On the left-hand side of the page, you see what we're able to do with that data. Just as one example, to help a fleet manager, we can show where the location is of all the trucks. We can drill into one of those and see also what the whole trace route would be for that vehicle. So next slide, please. So here I'm just showing more things that we do with the data, you know, be able to create dashboard views and provide insights really in real time so that fleet managers can manage these vehicles. Artificial intelligence came into the picture for us with one of our first large customers that had a data science group and that was working and building a predictive algorithm. These data scientists wanted us to take the algorithm and operationalize that so that not only are we doing basic things like alerting on specific types of events that are occurring, but that we could begin to do prediction. So we went through the process of integrating really a data scientist work, a data scientist that had been doing work using fairly traditional tools and worked it into our processing pipeline for real-time prediction. And although that probably sounds pretty straightforward, we actually found that there was quite a lot of issues with operationalizing that work and making it all run performantly and in real time. So that is really what sparked our interest in learning and beginning to understand the various types of, you know, machine learning and deep learning techniques so that we could be more engaged in that process with our customer and begin to take a part in developing predictive algorithms. So one of the technologies that we took a really strong interest in was TensorFlow. And Joe's going to go into TensorFlow a little bit more, but just on the very surface, it's an open source project by Google that's getting a lot of traction across really all the clouds and in many environments. People are really excited about what it's able to do and some of the models that are being shared and provided throughout the industry. So let me just give you an example of prediction here as it pertains to fleet management. If you think about all the data that we have, information, we sometimes call them features, that would allow us to predict a vehicle fault. What we want to do is take all that data and build a prediction model. So if we take enough examples of a fault that occurred and we look at all the data, all the inputs that we had prior to that fault, we can potentially start to build up a machine learning model that can do a very effective job at predicting a particular type of failure. So the types of input that we can use in this prediction are I'll look back for things like ambient temperature, specific vehicle events that might have been reported by the engine or other equipment, fault codes, for example. We could look at things like road surface types or elevation changes and characteristics about the vehicle, like the total number of miles that have been driven on that vehicle. Things like that all are inputs which can help us to do a model that can predict failure. And the interesting thing about machine learning as you get into it is you start to realize that really what machine learning algorithms are doing is taking all this data as input and really doing things that as humans we really can't sit down and write an algorithm to do. And in some cases we don't really fully understand why the prediction occurred as it did and what inputs were particularly useful in making the prediction. So if we go to the next slide, I'll just run through a few more examples here of where we've gotten started with machine learning and found it to be really useful. So we have a customer that, again, this started as an IoT project because they have existing product that does visual inspection for manufacturing companies. And what we're doing is working with them to envision what the next generation of this product might look like. And the product that they have today does some prediction, but it's not using modern techniques. Before even getting there, the data right now is not being transmitted to the cloud. So they don't really have the opportunity to take all the data in anything near real time and analyze the performance of machines that are out in the wild, with manufacturers. So again, our first opportunity is really in IoT. Let's get the data into the cloud so that it can be used for really straightforward kinds of things. And then beyond that, it's with machine learning. How could we build a more effective machine learning model to predict, to do quality control really on product coming down the line, so that we could kick out product that is not that's not meeting the quality levels. And so we're working with this customer to really do training around quality of a particular product. So we're looking at things like, is the label affixed properly? Is the level of the product within the container, does that look correct? Anything that we can see that would be abnormal, we can predict at a pretty high level or pretty accurate level whether or not it's a good product or not. Let's go to the next slide. So, and just to take a very different type of use case, here's one where this is in the legal space where we're looking through and processing legal documents. One thing that's really challenging about legal documents is that they're very long and it's very difficult to do a search and find the documents that you're looking for. So what this particular proof of concept was about was extracting meaning out of OCR documents. And so we're able to take PDF documents, OCR the documents, and then use various techniques, not just TensorFlow and machine learning, but we're using, for in this case, Google Cloud Vision to do text detection. As I mentioned, we're using machine learning for things like n-grams and linear modeling. And we're using Google Cloud Natural Language API to analyze syntax and extract entities like persons, organizations, locations, things like that. Next slide. So I've just tried to take you through some different examples where we've started to apply machine learning. There are some very different use cases, from vehicle logistics to manufacturing to legal documents and documentation. I'll go through some other examples later. I'm going to turn it back over to Joe so we could do a closer look solving problems with ML.
Thanks, Paul. So how to frame an ML problem. The key to understanding an ML is what it can and can't do is realizing that all supervised machine learning is to correlate two data sets. You have an input data set that represents what you know, and you have an output data set that represents what insight you want to gain. The learning algorithm job is to find the correlation between the two. So rule number one in machine learning is don't build a model if you don't have to. So on the left, we have the ability to build your own machine learning models, but on the right-hand side, the pre-trained models are models that are available within Google Cloud, and there's 8 cloud APIs that we have available, and is continuing to grow. The Vision API is something I'm gonna go dive deeper on the next slide. Speech converts speech to text. The Jobs API helps employers find employees. The natural language processing is what Paul described, finding sentiment of the sentence and sentence structure. The Translation API converts one language to another. Video Intelligence API makes video searchable and discoverable by extracting metadata about it. So for the Cloud Vision API, it has different arguments that you could pass. It can do facial detection, logo identification, label identification, explicit content detection, OCR, optical character recognition, and landmark identification. So I'm going to show a demo of this. So if I click on the cat photo, what's going to happen is that we're going to show a cat, and it's going to give a label that it says this is cat, and it's 99% confident that it's cat. But if you look further down, it says it is British semi-long here at 87% confident. I did not know that existed. That's an example for labels. Now I'm going to show off OCR. It's going to take a street sign, and within the sign itself, it's able to read the text and display it for us, the tree kangaroo. Next is facial detection. Taking a group of people, it's able to, we turn on the label features, but we are going to turn on facial detection, where it's going to identify the sentiment of the person. So it will draw polygon boxes around the person's faces. And for person one on the upper right-hand corner, it's not really showing any sentiment that is found. For person two, to the right of person one, is showing that the person is joyful. Next is, we'll go down here, is landmark detection. So given that this picture by itself, Google is able to identify the latitude and longitude of the photo and tell you Citi Field Stadium. Lastly is logo detection, taking a photo and it's able to tell you that it's the Android logo. So let me go back to the slides. So that's a little bit about Cloud Vision API. So when unstructured data accounts for 90% of enterprise data, and when we think of structured data, we're thinking spreadsheets that are neatly organized into rows and columns. But it doesn't have to be that anymore, because we have unstructured data like emails, call recording, images, and videos. And you could get valuable insight out of this data by using some of our machine learning APIs. You could feed the emails through our natural language processing. You could feed your call recordings through our speech API and your images through our vision API. And when you're training a model, and if you need data sets, there's a tool of, there's a site of Kaggle, and that was recently acquired by Google itself. They have over 1,000 data sets that you can use within your projects, and it'll help you out with your machine learning models. So to get started with machine learning, our chief data scientist, Casey, has identified 12 steps. And what we see is 70% of the data is, as mentioned, is between steps 2 through 7, getting the right data and finding patterns within data. So I'm going to turn this back over to Paul.
All right, thanks, Joe. So I'm going to share another use case that Agosto's been working on with a customer. Just trying to give you a good flavor for the kinds of things that we're doing with machine learning. Again, this project started out as an IoT project, and the customer in the beginning really wasn't really thinking about machine learning. What they were working on was devices that could be used, sensors, in feeding and drinking areas, in barns, and ear tags on pigs with sensors so that they could look at detecting animal behavior. And this is in clinical and basically just in the area of detecting unhealthy animals. And so the first phase was really about what Joe had in his list of ML, was getting the data right. So just starting to find some patterns in the data. So in this first phase, we wanted to prove out that we could, first of all, that the devices work properly and that we could collect the data, and that we had something here. What we were thinking about is there something here that we could apply machine learning to that could really help facilitate prediction of an unhealthy animal or an animal in some kind of a particular state. So next slide. So I've got some images here just to help you get a better idea about what this solution is about. So here you see an ear tag, the one with number 153 on it. That's a standard ear tag that's used in the industry, and the difference is that we put sensors on that ear tag that contain a board with sensors and Bluetooth connectivity. Then if you look at the lower right, you can see where we have beacon devices that are attached to the eating and drinking areas. And with this, we're able to detect both the movement of the animal from the ear tag and changes in proximity to the eating and drinking areas. And so with that, we're collecting a tremendous amount of raw data. And what we helped our customer to do is take and be able to begin analyzing that data to just really take the first step to prove out, is there anything here where we can see and potentially harness these patterns for use? And so what they did was they looked at the data, and in this case, what we were doing is moving the data right into BigQuery, so they could query over a huge amount of data, and they could look at corresponding video to understand the data as it corresponded to particular actions. So next slide. So here's one example where we're just looking at accelerometer data. We've got XYZ data. And on the next slide, here you can see that we've started to mark and identify specific behaviors. And this again was from lining up video segments with the timing of the sensor data. And so in this first proof of concept phase, we were able to begin proving out that we really could. It appeared that there were very notable patterns to these different types of behaviors. And since then, they've gone through and further isolated out particular behaviors that are of interest. So in the next slide. So like our IoT rapid prototyping phase, we have an ML proof of concept phase. And there's a lot of detail on this slide, but just to say that basically what we're doing in these early phases is really looking at the potential of a problem that we can solve. We're defining and preparing data. We're developing a process for building and tuning an ML model. And we're trying to get a first look at what our error rates might be. In other words, is this something that we can apply machine learning to that can really help us in some way to solve a business problem? And we begin to envision what the next steps might be for either improving results or improving throughput or working on particular feasibility kinds of issues. What it's really aimed at is helping our stakeholders to assess the results that they might get in moving, they're moving forward with some kind of a business problem. So in this project, we've started to do some, we've done some basic IoT work, and now we're moving into ML proof of concept work to really look at how we could take a lot of technology and raw data and transform that into some kind of a go-forward plan for our customer to solve a specific problem. Next slide. So I'm going to turn it back to Joe. He's going to go into some detail on operationalizing an ML solution, and then I'll have one more use case to talk about where we've begun to operationalize an ML solution.
Thank you. So there are tools to make machine learning faster, fun, and easier. And what I mean by faster, good tools can help automate each step in the applied machine learning process. That means that the time to go from ideas to results is greatly shortened. Easier is you can spend your time choosing the good tools instead of researching and implementing techniques to implement. The alternative is that you have to be an expert in every step of the process in order to implement it. That requires much deeper experience and research to understand the techniques. Fun is that there's a lower barrier for beginners to get good results. You can use extra time to get better results and work more on the projects that you're spending your time using the tools to get the great results instead of building the tools. So building a machine learning model requires three things: data, compute, and talent. And assuming that you got the people and the data, let's talk about how to use the framework and the machine learning computing created by Google. Here we see 6 popular machine learning frameworks as measured by GitHub stars. And you can see that TensorFlow is by far the most popular. The popularity of TensorFlow isn't just a stat. It means that you have a vibrant community of fellow developers help reach out for help, the most reference implementations to pull from to bootstrap your projects, and also a vibrant community of open source contributors to make sure that TensorFlow algorithms are updated frequently to keep pace with the state of the art. Here is a TensorFlow output of an execution graph. The tensor board allows you to visualize what's going on within TensorFlow itself. So within Google Cloud, we have compute. Because compute is computationally expensive and training time is often the greatest barrier to progress. That's why precisely neural networks, even though they've been around since the 70s, they've only come into favor recently because of compute. Only compute has caught up with the demands of the neural networks. And this is why machine learning and cloud computing go hand in hand. Google Cloud Machine Learning can make a previously intractable problem solvable by solving the compute bottleneck problem. So we have Cloud Machine Learning Engine. It's essentially TensorFlow as a service. It lets your data scientists just worry about data science. We take care of the infrastructure, monitoring, logging, and versioning. Most importantly, we take care of the horizontally scaling, which anyone who has deployed and maintained a Hadoop cluster knows is no easy task. And when you're done with training, it's just a few clicks to expose a trained model for prediction via a REST endpoint. Or you could download the model and deploy it anywhere you want, as on a mobile device, like the Hotdog app, or on-prem. There is no lock-in, reaffirming Google's commitment to open source. And when you're running within Google, you get also access to some of our custom proprietary hardware, which is called our tensor processing unit. It's a fast chip to help you learn. As you can see, the comparison between a K80 versus a TPU, 9 teraflops versus 180 teraflops. And this is something that we've been using internally at Google for the past 1.5 years, and now we're making it available on the cloud platform. So putting this all together, how does a machine learning application look like? If we were to take this, this is what a result can look like for your company. These are the individual building blocks assembled together. So if you have your inputs storing within Google Cloud, as in within cloud storage or BigQuery, then we have our processing using our data flow or Dataproc, which is essentially Beam and Spark and Hadoop. Then you could train the model using our Cloud ML, distributed training, hyperparameter tuning within there, and then storing the results and everything within storage, and deploying it back within Cloud Machine Learning so you can access the data and the output. Now back to Paul.
Okay, thanks, Joe. Well, I've shown you a number of projects that Agosto's been working on where we've applied machine learning. I've got one more I wanted to share with you today. So Force Multiplier is a customer that's in the business of school bus safety. And for school buses, among many concerns, one of them is that when students exit and enter the bus, the stop arm goes out. I'm sure you all know the rules here that a car is supposed to stop and allow the children to cross the street safely. Surprisingly, a lot of cars blow through these stop signs, and it presents a real risk to children. So Force Multiplier has equipped buses with video cameras, and they capture all the video from the bus as it's running. They also have a device on the stop arm that collects the open and close events. So they've got timing data on the open and close events. Because really that's the part they're interested in the video for determining if there's some kind of a violation. So the way it worked before we got involved was that they broke this work into 2 phases. So one is that they would look at the video segments from when the stop arm was open, and they would have a person evaluate that to determine if there's any potential violation, and then anything that was marked for further review would go to a second stage, and there they would analyze the video and see if there's enough information that they could submit to law enforcement as part of an evidence package for ticketing. So what our objective in this proof of concept project was to determine if we could build a machine learning process or a prediction process to determine if there was a violation in an automated way. So, and again, we're looking at only the segments of video where the stop arm is open. So we took this customer through a proof of concept phase where we were able to combine a lot of different techniques, computer vision techniques, with machine learning to build up a prediction model that the goal was to predict, to see if we could be more accurate than what the human workers could be, either more accurate or in the same vicinity, so that it would make sense for them to look to automate that first stage. And why this is really important to their business is that for scaling purposes, it's difficult to scale when you're dependent on just hiring more and more people. So they thought there would be huge value if they could figure out how to automate the first stage of this process that they had. So we took them through this process and were able to prove out that we were actually, even within our proof of concept phase, slightly more accurate in predicting a violation than the human staff was. And so we're moving now into a phase where we're looking at how to operationalize that. So a lot of the challenges that Joe was talking about, we're now working on how do we insert this machine learning process into an existing process that our customer already has. So they already have a process for ingesting the video data and processing the video data. What we want to do is insert this prediction element and replace a certain part of their whole process flow. So we're now looking at how do we set up an API that allows them to make a request for analysis for prediction, and really just looking at the whole flow, including how do we retrain the model and how often do we need to retrain the model, and do we need different variations of the model based on geography or maybe even down to school district. We certainly know that, as an example, for the north where there could be snow, we need to test and possibly have a specific model around that vicinity versus the south where we're not likely to see that. So it's been interesting, not only just working through this problem and proving out in proof of concept that we could solve this problem, but then looking at what does that next phase look like to further improve the performance of our predictions, and also how to operationalize that work so that they can have this running in a real-time operational way. And last, how do we retrain or update or improve our model with the additional information that we're collecting over time? So with that, I'm going to turn it back to Christy. She's going to just do a little bit of wrap up before we get into the questions that you have all submitted.
Okay, great. Thanks, Paul. So again, we are offering a complimentary machine learning consult for any of you that have attended today. So Joe, if you want to switch to the next slide, my email address is up here. So feel free to contact me directly and I will get you set up with our ML team on both Google and Agosto's end. It will give you guys a little bit of time here to jot it down. And you can also, like I said, reply to the webinar invite as well. And that works perfectly fine too. Okay, so we've had some questions come in through the chat box here. I'm going to start with probably a general one for the audience here. Paul and Joe, first question is, do you store our data when using any of your managed ML APIs?
Thank you. We do get that question a lot from a lot of customers and companies who are worried about Google using the data for their own, for our own machine learning models. And any data that's submitted to us through our machine learning APIs will not be used to help train our models in any way. Your data is your data. We'll not be using your data in any way. It's completely separate than what Google is using.
All right, perfect. Another general question that came in through here, there's a lot of noise in the ML space. How do you suggest that I get up to speed on it? Yeah, Paul, do you want to take that one?
Sure, yep. Yeah, that's a good question and kind of a complex one, because I think people are coming at this from a lot of different perspectives. One is, I'm a product manager and I need to understand how machine learning could enhance or how it could apply to improving my product. An architect is really just wanting to know more of what's technically possible, and at a high level, how does this plug in? How complex is it to do this development? Do I need to build a machine learning model, or can I use pre-trained models or APIs that are provided by Google or other providers? And then last would be an engineer who they really need to figure out how to do it. How do you build a model? What technique should I use? What combination of techniques and technologies should be applied to solve the problem? So what I've found for our company is just pointing people at different resources, depending on what they're trying to get out of their coming up to speed process. And one really good resource is Google I/O videos from 2017. There's a lot of content on machine learning and on the various APIs that are available. And another one that's a very good resource is Coursera. I found a lot of good introductory kinds of content there. Some are aimed at a much more technical level, some aimed more at just understanding concepts. So if I knew more specifically what the role was of the person that asked the question, I could go into more detail, but that's just some general guidance on how to get started.
Great, thanks for that. The next one that we have here is a little bit more targeted. So the question is, what successful methods have you seen with clients where they've incentivized their annotate raw data, in particularly images? For example, radiologists resist reviewing old images that are no longer clinically relevant to any patient because it isn't financially worth it.
Yeah, I can take that. I can take a crack at that one. So I don't know that I have a great answer, other than a big part of our job when we go in to start a project is to really figure out where is the information and how do we extract it, or how do we pull it out in a way that could be useful to us in doing a proof of concept model. And as you mentioned, there's a lot of data that's perhaps available, but maybe it isn't relevant. And so we have to figure out who can really help us tag the samples if they're not already labeled. Who can help us with that labeling process, and how can we do that in an efficient way, so that we can collect enough data to actually build enough of a model that we can start to look at error rates and understand if this can be useful to solving a particular business problem. So it's a great question. I don't know, Joe, if you have any more to add to that, I'll let you take a crack as well.
Yeah, nothing much more to add to that. I was just having a little hard time. Would it be possible to repeat the question?
Yeah, sorry, I heard that my connection was broken up. So the question is, what successful methods have you seen with clients where they've incentivized their domain experts to label or annotate raw data, in particular images? For example, radiologists resist reviewing old images that are no longer clinically relevant to any patient because it isn't financially worthwhile.
Oh yeah, we also seen that to add on to that, I mean, incentive-wise, we've seen certain companies that are looking to use, we have a commercial data set program where they want to upload old medical image data that's non-identifiable and have labels around it so that they can become more of a profit area as well. So we've seen certain companies going down that route as well for it.
Okay, great. Thanks for that, Joe. Another one that we got here is talking about the Hadoop environment. Do we need a Hadoop environment to do ML, or can we learn from SQL databases?
I can start answering that one. I'll let Joe chew on that one a little bit too. But you don't necessarily need a Hadoop environment to do ML. Again, the data inputs for machine learning are so varied that it just depends. It's really kind of in the last question trying to figure out where is the data and how do we transform it into data that we can use in a machine learning model. And it could be that there's a lot of data that's contained in databases, or it could be that it's image data that's stored in some other kind of a system, and we need to figure out how to extract that for the purposes of machine learning. So it's really varied depending on the type of data that we're talking about.
Yeah, and I would agree with you that you don't need to have Hadoop to do ML.
Okay, perfect. Another question we have here is most of the examples are around visual and verbal models. What about organizational decision-making models?
Well, let's see. I'll take a crack at that one as well. So the question there would be, if we're going to use machine learning, where is the data that would show good decisions versus bad decisions? Because what we're trying to do is figure out how do we build up a model where we can take sample data and we can say this is a good decision and here's a bad decision. So what are the data or the attributes or the outcomes, and can we get enough samples of that to use machine learning to build a prediction model for around decisions? So in retail, it might be that we want to determine if a sale that we made online was a good one. Well, what does good one mean? That might have to do with profitability. It might have to do with shipping costs. It might be kind of a whole combination of factors that we would say that was a worthwhile sale that met our goals. And so you would have to take the data from whatever the inputs were, and you would have to train the model to say this was a good transaction, this was a bad transaction, or this was a profitable transaction, this was an unprofitable transaction. And machine learning works if you have or can collect up enough samples that you can use that history of samples that you've collected to do prediction. Joe, anything else to add to that?
It's kind of a little bit of a sidetrack. When I think about decision, I also think of like chatbots as well. And you can use a company that we have. It's like when you type an answer, a type of question, you get an answer, and that can be done through machine learning. And a company we recently acquired is API.ai to help out with these chatbots that help you enable and get you going quickly on a machine learning chatbot process. Somewhat of a sidetrack answer, sorry. But I agree with what you're saying. You're going to need to have the labels to these decisions.
Great. All right, I'm going to ask one more question, and then some of these other ones here are pretty specific and pointed, so we'll reach out to you separately to answer them. But the last one we're going to go for right now is ML versus automation. Does ML imply continual ongoing refinement based on feedback from the system ad infinitum, or can it just mean to a point?
That's a good question. There are some things where you could build the model and you wouldn't likely need to have any kind of a strategy around retraining or improving the algorithm. If I just take something really simple, like I want to have a machine learning algorithm that can tell me a particular color, and let's just say I've got the basic rainbow of colors. Once I build up that model and I prove that it works very, very well to a really high degree of accuracy, I don't necessarily need to go back and retrain that model. However, if I have things that are more dynamic, like maybe in my retail example where buying behaviors are changing, competitive pricing is changing, shipping costs are changing, all those kinds of variables, then I may need to have a process to go back and continually retrain my model so that it's kept up to date. So the answer is no, you don't necessarily have to have an ongoing training process that never ends, but it really depends on the specific use case.
Yeah, I mean, I concur with that as well. It's just, yeah, that sometimes you have to keep up to date with some of the machine learning models of identification of maybe particular photos or whatever it may be.
Great, and I'm actually going to ask one more general question that we just had come through, and then we'll wrap things up. How big do you have to be in order for ML practices to be feasible?
Let's see, how big do you need to be in order to ML? And I assume we're talking about organizational size here. I don't think there's really a big or small there. To me, it actually has to do more about the data and the problem and the data that's available, and the complexity level of the potential solution. A solution where you're leveraging ML could be as simple as using existing APIs with pre-trained models, which really is just an API call. I can have a very small organization with some data or an ability to collect data and develop something that's very effective and that has a huge return on investment, or it can be extremely complicated. So I think there's a whole range, but I don't think there's really, I don't think size of organization is necessarily a really huge factor in all this. I think it's more about the problem and about the data that's available, to apply toward an ML type solution.
All right, perfect. Looks like that is all that we have for right now. So again, if you want to get into a deeper conversation about your specific company, you can send me an email and I will connect you with the teams there. I'll put my email one more time in the chat box for you here as well. Oh, there it is. Thank you, Joe. And thank you so much for joining us today.